So we're very glad to welcome you all to today's webinar. Like we know, the title of today's webinar is Exploratory Data Analysis and Non-Compartmental Analysis, or PKPD data. And this happens to be the fourth in the series of webinars run by Pharmacometrics Africa, which is a non-profit company based in South Africa. And the goal of Pharmacometrics Africa is to build pharmacometrics capacity in Africa. By the way, my name is Adeni Olagunju, and I'll be your moderator for today's webinar. I'm currently based at Obafemi Awolowo University here in Nigeria, where I work as a lecturer and a Wellcome Trust Fellow, as well as an affiliate of the African Academy of Sciences. I have a PhD in pharmacology from the University of Liverpool in the UK. My primary research interest is infectious diseases pharmacology, and I focus on generating PK and PD data in special population cohorts in Africa, including in pregnant and lactating women. So today I'm very pleased to introduce our speaker for the webinar, Dr. Samuel Moksasi, who is a Senior Director of Integrated Drug Development at Satera. Satera is a very important company when it comes to PK/PD modeling all around the globe. Since 2007, Samuel has been responsible for implementing model-based drug development to support regulatory submissions and decisions. His team has successfully secured numerous approvals from the FDA, the EMA, and Japan for numerous companies. And since 2014, he has been dedicated to the Knowledge Integration Quantitative Sciences team at the Bill and Melinda Gates Foundation to support various programs for the Maternal, Neonatal, and Child Health Initiative. Samuel, as you will see very soon in today's webinar, has a very strong passion for teaching, and is currently an associate professor of pharmacometrics and clinical trial design at University de Montreal and Lebanese American University. Samuel received his PharmD from Lebanese University and a PhD in PK/PD modeling from University de Montreal. He has co-authored well over 100 scientific communications and supervised several postgraduate students. He has a couple of open source R packages which focus on insightful exploratory data analysis. So it is my pleasure to welcome Samuel, who is our speaker for today. But just before I hand over the mic to Samuel, just a couple of housekeeping items. The first one is to tell all of us that today's webinar will be available on demand after the live session, and is going to be posted on Pharmacometrics Africa website, and that is www.pmxafrica.org. And all the resources associated with today's webinar would also be shared on the same website. And then the second item I have is that you notice you are currently being muted, and the purpose is to prevent interference during the session. But if you have a question, which we strongly encourage, so please feel free to use the chat box in Zoom to post your questions, and we'll try as much as possible to answer those questions at the end of the session. And you can also send any question that you may have at the end of the session by filling in the contact form on Pharmacometrics Africa website. And lastly, we would like to encourage you to share today's webinar with your social networks on Twitter, on Facebook, and LinkedIn once you receive the recorded webinar thereafter. So without any further delay, I will now hand over the mic to Dr. Samuel Moksasi, our speaker for today. Samuel, please.
This webinar to introduce you to exploratory data analysis as well as non-compartmental analysis of PK data. Thanks for joining. So today's agenda will be basically, we will start with exploratory data analysis, methodology, how to look at your data, and ultimately how you generate insights and generate hypotheses from first looks on your data. Next, we'll cover non-compartmental analysis methodology, and we'll keep it to the basics, some assumptions, the pros and cons, and we'll really tackle the single dose simplest cases for today. I will also cover when NCA is used, how it's used, and brief comments on interpretation and reporting. So you will know what we won't cover today is like some advanced, more advanced type of non-compartmental analysis, like for steady state, multiple doses, sparse PK, NCA for toxicokinetics, and what we will do next after we run NCA, like statistical analysis of bioequivalence or ratios, and so on. So today's focus will really be as an introduction on EDA and NCA. So first we'll start with exploratory data analysis. And as you will see during this webinar, we'll have like some background and theory in the beginning, and as next section, it will be a live demo of various tools that we will be using to illustrate the concepts. So what is exploratory data analysis? So exploratory data analysis, or EDA, is a kind of an approach that has been pioneered by a famous statistician, John Tukey. He wrote a book in 1977 entitled Exploratory Data Analysis. So basically, this work, which now is highly cited, was telling people, don't jump into analysis right away. Please look at your data, make sense of it, to make sure that you don't miss important feature of the data that might not be evident from a regression analysis, from slope, intercept values, from numerical values. So a statistical model can be used or not, but primarily it is seeing, looking at your data before the formal modeling and hypothesis testing task. And we are lucky in our days because we have many, many tools that render the task of plotting, graphing, looking at your data quite straightforward and user-friendly. So I hope with the coming slides, I will convince you that that's how we should always start our data analysis. So what is the goals of EDA? Usually it is to confirm our prior beliefs. Is what I see in the data expected? Is PK concentration increasing when dose is increased? And sometimes we get a surprise. Maybe we have a saturation and we have a disproportionate increase that we can directly see it, or we only see it in a few subjects and so on. So it's really, one part is to confirm prior belief and maybe discovering new features that we didn't expect, and then digging further by slicing and dicing the data more, by focusing on specific subjects, for example, to try to detect and know why we have this weird, unexpected behavior. So through EDA, we can also detect through some techniques nonlinearities or linearity. We can also choose to overlay a simple statistical method. It can be a mean or median overlay. It can be more sophisticated, like a Kaplan-Meier curve or a logistic regression line. And all of it is to detect trends of the data versus time or other variables. And as I mentioned, we want to contrast/compare data slices. And by data slices, I mean that you might have several dose levels, or what we will see today, we will have a study with different formulation levels. So we want to compare across formulation. And we can do that through visual or tabular summaries that we will present. And sometimes when doing EDA, we can find some data gaps. For example, we can find that we had maybe 80% of our subjects as men. We can discover that some range, we missed a good age range when we plot, say, age distribution and so on. And it will help us by finding data gaps. It will help us plan and formulate our next data generation trial. And a famous example of the value of plotting data is what's called Anscombe quartet example. So that's very, very commonly used to illustrate why EDA is variable. So here we have 4 different plots, and it's plotting Y versus X. And actually what they all share, they share the same summary statistic. So if you compute a median, SD, mean, etc., you will exactly have the same values. So if you have done the classical or the old table of data summaries, you will miss the trends that are evident by plotting the Y versus X. So here I'll try to use a pointer. So I hope you can see my pointer. So here we can see that first it's like a linear trend, but some deviation around the line. Here it's a non-linear type of curve, quite different from this one. And here we might have some outlier points that's different from the rest. And here we have all points at one value and 1 point very far. So by looking at the data, we can really detect patterns and things that are very hard to detect through statistical summaries. Later on, people has built R packages that can even generate quartet-like data, where here you can see we always have to the third digit same mean, median, SD correlation, but the shape of X versus Y or Y versus X quite different, can be even a dinosaur, has been done for fun, but just to illustrate that, yeah, don't just trust the numbers, you need to look at your data. So, and of course, we should not forget that one of our primary tools for EDA is a familiar Excel. So Excel enables us to do a simple plots, simple tables, and we'll see it later on. And it enables highlighting, it enables some contrast. So we'll cover it, but we will also show in the demos more advanced tool. Like here, I'm showing Data Explore, which is part of the Monolith suite. So today we'll see some features of the Data Explore, of PK Analytics, and some are open source tools as well. So in this section, I will illustrate some EDA concepts. Regardless of the tools that you are using, the concepts are always the same. So here, to make sense of your data, you want, maybe here we have a concentration versus time, and we are joining each subject profile independently. And also here, it's a 3-way crossover study. So we want each occasion to be a separate line, not just by subject. So it's by subject and occasion. And to be able to contrast male and female, here we separate it, we split. And here the jargon can be slightly different between software/tools. Some people call it splitting, faceting, trellising. Ultimately, it's the same. It's just showing different slices of the data side by side. That also has been called small multiples. So here we are contrasting male and female, showed in separate panels. And we have concentration versus time, its subject, occasion, a line. And one nice feature of that Explore, when you highlight a subject, you can see that the other occasions are also highlighted. So I hope you can see it. But here I zoomed in to show you that when you highlight one subject, the other occasions from same subject will also be highlighted. So you can quickly see what were the 3 different occasions and 3 formulations for the subject, which is very nice. And it's like a technique called highlighting, which is common in EDA. So another technique here, I'm showing a snapshot from an R package that I wrote called GG Quick EDA. So same approach. One additional concept I'm showing, so in addition to the splitting, faceting, call it what you want, by form, 1, 2, 3, each subject is a line. I overlaid a mean confidence interval. So here we can, we can see that, yeah, that was the mean PK profile for formulation 1, 2, and 3. And we can immediately see that formulation 1 had a lower mean profile, we'll see with NCA maybe lower AUCs and bioavailability. That help us generate some insight. And other tools also enable you to do the same, like Phoenix Nomen that's widely used in NCA. So also, another valuable technique to explore your data that will show live is what we call scatterplot matrices. So you plot many variables. Like here, we are plotting the covariates, age, height, weight, the formulation, the gender, the race. And it helps us see what are the things. So for example, here it's age versus height or age versus weight, or the reverse. Weight versus... Hello? Hello? Can you still hear me? I heard some comments.
Yes, we can hear you loud and clear, Samir.
Okay, great. So please, if you have questions, please fill in the chat box or just ask. So here we are showing the various correlation or relationship between the various covariates. So here, for example, in a formulation comparison trial, we want to see if age is different. Here we can see for female. Hello? Is there a problem with the volume?
No, the volume is fine. It could be a local problem with that attendee. Please go on.
Okay, so here, for example, we can see that weight in male, as expected, was higher. So that's a box plot of male versus female of weight, and so on. So another way to look at it is famous summaries, but again, you might miss patterns by only looking at the summaries. So try to always do plots and tables. So here is also a default output from PK Analytics or Data Explorer, where you have some information about the covariate, like how many formulation 1 to 3, how many male, female, what were median Q1, Q3 of continuous variable like age, height, and weight, and so on. Just so you know, when you have multiple occasions, IDs are counted multiple times. So here the trial didn't have like 64 different subjects, but it had 63 different PK profile. Of course, each subject had up to 3 formulation. So that's not the number of total subjects. So you need to be aware of that, depending on the tool you are using. And I will show you during the demos that you can use GG Quick EDA as well to do some of these Scatterplot matrices, slightly with more feature. Like here we can have a correlation coefficient and PK analytics as well, but not by a colored variable, by formulation. And here we'll show you can have a confidence interval around the regression line. Some additional features, but they are very similar between the different tools. And in GG Quick EDA, I showed that you can quickly do a table, not only a plot, and you can split it here. I split the table by formulation. And here we see that we had like formulation 1, we had 23, and what were like the summary statistic by occasion. And for the categorical variable, we have the percentages as well. So we have slightly more additional statistic in this table. So back to the goal of today's webinar, which is focusing on PK analysis. So common EDA techniques for PK is to show individual profile of concentration versus time. Since last dose, especially for NCA, because we are not modeling the multiple dose, we are really taking it profile by profile. And of course, we want to make sure we illustrate the study design. So we want to grow by occasion formulation. And we want to know maybe some additional feature on the profiles as subject. As the sex, the dose level, from which cycle, linear and log scale, etc. And we'll illustrate some of this in the demo, in the live demo. So as I showed, we want sometimes to overlay mean profile. Maybe we just want mean profile without the individual ones, log linear, and so on. And sometimes, for example, when we have only troughs, you might not want to join with a line. It gives a false impression that like between the troughs value, there is like, there's no peak or no dose increasing. So you need to have some of this consideration. Overall, in EDA, you should always think about whether you want to overlay, whether you want to split the display, whether you want to have a statistic like a mean, median overlaid, and sometimes very important how you order the various panels or small multiples of your plot, because it will help you detect a pattern faster. And I will show an example of that. And for your reference, I've included a set of links to a very nice mini course available on the University of British Columbia website. They have a lab that does a lot of research on visuals and how to communicate using various mapping of colors, shapes, etc. So for those interested, you can really refer to this material to see how best to build a visual plots that communicate your idea. So here I just repeat what I just said in this previous slide. Many organizations use this concept, not necessarily like in pharmacometrics or PK analysis. Here, just for fun, I show you that the BBC heavily use visuals to communicate complex ideas. They also have their own ggplot team and a GitHub page and some standards on how to choose big colors up to the tiniest detail. This can be important. So that concludes background or theory on EDA, and we'll tackle now briefly the non-compartmental analysis. So maybe some of you has done population PK or some form of PK analysis, but not necessarily NCA. So today I hope I will convince you that NCA is an important toolbox that you can use and is being used in various drug development stages. So NCA is a method to analyze PK data that we all know is collected through different stages of drug development. And once we compute the NCA PK parameters, we want to summarize it and make sense of it. And NCA is used to answer key clinical and drug development questions like, what is the extent of drug exposure with a given dose? Does the exposure increase linearly with dose? So we run maybe dose proportionality analysis On the NCA output, the example we'll see today is about comparison between formulation. When we have urine data, we can determine what is the renal contribution to total drug clearance. And the last question, does different fixed drug combination of 600 milligram rifampicin provide similar exposure? That's a real data example where which Dr. Pillai forwarded to me that we will be using. That comes from real data from South Africa, and it will be good to see some of the challenges, I would say, that might arise with real data. So NCA enable us to estimate PK parameters of interest. So in addition to the modeling parameters that some of you might be familiar with, like clearance volume, we have AUCs, we have Cmax, Tmax, and half-life, maybe accumulation. So I will cover some of the definition of this parameter and some of the associated interpretations. So to me, NCA is kind of a modeling strategy that carries fewer assumptions than like full PK compartmental modeling, if you want. But we need to be aware what are these assumptions, when they hold, and when this methodology can be used or not used. So also another concept or fact about NCA, it's heavily used in supporting regulatory modules to describe novel drug application PK. So if you Google any FDA, for example, clinical file review. So when you are a company, you submit your data to FDA, the FDA issue review the application, and one of the reports they issue is the clinical file review, and you can see that here you will have this PDF that's straight from the FDA website. You will have it in the Dropbox. So you can see there's a whole section about clinical PK, which is heavily based on NCA, Cmax, Tmax, AUC last, AUC 012, some statistic. So this slide is really to show you that this methodology is used in drug development. It's very important. In addition, of course, later you can do modeling, you can do simulation, but we always start by simple EDA and NCA. So as a summary, NCA is used in the various drug development studies, whether it's preclinical, toxicokinetics. There's various phase 1s like MTD, first in human, the single ascending dose, multiple ascending dose, formulation effect, and so on. DDI, food effect. And even in phase 2, we can use some NCA on PD data, like area under the efficacy curve, and so on, which I won't cover today. I just wanted you to be aware that these methods exist, and we can tackle it as a question if you are interested. So a typical NCA workflow is you get the clinical protocol, you recruit volunteers or patients to clinic, you collect some data, you provide, you measure PK, you have some analytical reports that quality assure whatever you measure, and then you build some data. In a non-industry setting, maybe you don't do all these steps. Maybe instead of SAS data set in CDISC format, you have an Excel file. But that's fine. So next step, as per regulatory guidance and as per good statistical practices, you should have an analysis plan in place before looking at your data. So you have an analysis plan, you bring in the data, you do your NCA, which is the focus of today. And once you did the NCA, you might want to do some, summarize it using tables, figures, maybe do some statistics and tables up to reporting. So the part we are really covering today is this part, which is just analysis as an introduction. So non-compartmental analysis is also called moment analysis, statistical moment analysis. So as a contrast to compartmental methods, or say PBPK type of PK methods, where you have many compartments, you have a brain, you have the liver, you have various organs and your big model. With NCA, you have fewer assumptions. You are really concerned about your input, whether you administered the drug IV or extravascular, for example, where you are measuring. So you got an observation from plasma. Sometimes might have a metabolite, you might collect urine. So, okay, you incorporate this information into your NCA, and you can compute variable parameter like clearance, so which is derived from the area under the curve. But this moment analysis is based on a mathematical and statistical theory that considers the time course of drug concentration in plasma as a statistical distribution. So think of it, you have an amount of molecules that are passing through a kinetic compartment, and its statistical distribution, which varies. Through this theory, the first, we have moments, so we have the zero moment, the first moment, even higher order moments that we don't use in PK. These moments will give us, on average, what was the concentration in plasma, which what we refer to as area under the zero moment, or AUC. So for more info, I also included one chapter in the materials that you can use. So for sake of time, I'm really covering the basics here. For more detail, you can refer to the books and references I will be providing you. So what are the NCA assumptions? So key assumptions for NCA is that things are linear, whether it's input, say it's a first order, it doesn't vary with time, like say Ka is super fast for 2 hours and it becomes super slow. Well, it can work, but what you will end up having is a mean absorption time, which is kind of average. It won't get into like the detail of it. Same transfer is first order, parameters don't change with time, and sometimes you need to acknowledge assumptions that no peripheral elimination. So if you do a literature search, you can see, you can say find extensions to NCA, like some of Leslie Bennett paper showing, extension to when we have peripheral elimination. So these are not widely used, they exist. There is some a whole body of literature on this moment analysis for more advanced methods, but they are not quite used routinely. People prefer compartmental models, which are more expandable and flexible in these more advanced situations, with time varying parameter, with clearance changing over time, auto-induction, auto-inhibition, and so on, time varying clearance. So here for your reference, I included some more detail about moment analysis, a Wikipedia link and a paper in Journal of Pharmacokinetics and Biopharm. That's the name of GPKPD before it got changed to Journal of PKPD. So it's from 1978. So what are NCA parameters that we compute and use? So here, for sake of time, I will try to go quickly over this to allow sufficient time for the demo. So here we have a bunch of a couple of measured concentration. For each concentration, we have an associated time. So here we measured 1, 2, 3, 4, 5, 6, 7, 8 concentration. And we can think of it as a PK profile, which joins them as a line. And Cmax is simply the maximum concentration, and Tmax is the time at which we detected the Cmax. So it's a very straightforward parameter, but they are highly dependent on the dose. Imagine that you didn't measure PK at this point, and you only measured this point here and this point here. So your estimate of Cmax would be probably this one, this guy, and Tmax would be here. So they are highly dependent on your design, on your time point of connection, but there is no assumption involved. It's really something you observe in the data you collect. Another important parameter with NCA is the terminal slope, also called lambda z. It's like it's the last letter, lambda z, it's the last one. And so you run a regression on your terminal phase, and you compute the slope, and your half-life is, you use log linear regression, and your half-life will be log of 2 of your slope. But there is many ways on how to compute, or what rules to use for your terminal lambda z. So, for example, how many half-life you want to cover, how many minimum number of points, like you don't want to use only 2 points because it won't be robust, or you don't want to include Cmax on your regression. You want to maximize adjusted R squared, so you try all possible combination of points and so on. So, and as we will see, that's a snapshot from Win-Nolan rules, and you will see here a snapshot from PK Analytics, possible rules. With the demo, we'll see how we can change it easily by subject, these rules, to exclude some points. For example, here, this point was excluded because it was out of like the trend of the linear phase. I hope you see this excluded point. And another important parameter is AUC, area under the curve, which and it's an integration method. So we want the area, how much, like this area really under the curve, as the name states. So how to compute it? So while there is sophisticated mathematical method like using splines and numerical technique, most commonly in NCA we use what we call the trapezoidal rule and variation of it, like log linear, what we use when constants are going up as in going down. But to explain to you, that's a profile. So here we have a concentration at time t and concentration at time t plus 1. So between each successive time point, we compute the area of a trapezoid. So this shape here is a trapezoid between t and t plus 1. And what is the area of a trapezoid? Basically, that's a formula. It's you compute CT plus CT plus 1 over 2. So that's the average of the two. And you divide by like the delta t. So basically, so that's from simple geometry. And then you want to do that for each slice. So here, and usually in NCA, unlike POP-PK, we want to add this point, time zero concentration equals 0 by definition for extravascular administration, because we want to compute this first area. We don't want to miss this area at the beginning of the profile. And we do this trapezoid up to the last point. So that will give us the AUC 0t. And the last part here, which is from time t till infinity, there is a formula or a method to compute. So if we want to illustrate that using a mathematical formula, that's how we write it. But it's simply the AUC 0t plus AUC from t to infinity, which we will illustrate in the Excel. So AUC, as I mentioned, we want to add time zero and concentration 0. And there is some assumption involving that we use this triangle at the last part. So it assumes that the last part is mono-exponentially declining, and which in general holds for PK. Sometimes it doesn't, but that's a common assumption we make. And ideally, of course, we want this part of extrapolation less than at maximum 20%, because otherwise there is high uncertainty. Like we need to sample long enough to cover 80% of the AUC. Sometimes not possible due to like a long half-life and other constraint. So we end up using AUC 0t instead of AUC 0nt. And that's a snapshot from the sector of the NCA analysis from Caruso and Weiners that you have access to. It shows you the various limitation of the various methods, and we'll see more in the demo. One note about the assumptions on BLQ data for NCA. They are mainly based on imputation. They are not likelihood based like we do in POP-PK most commonly. They are based on imputation, say what we do, and sometimes we have different rules whether we are early in the profile. So before Cmax, for example, we put 0, we assume it's 0. After Cmax, we might replace it by BQL over 2. And you can see or imagine that different people make different assumptions as long as you document it. And you'll see in the various software there is different options you can choose from. So, and of course, if you have half of your data is BLQ, NCA might be questionable, and you might want just to do modeling because there is a limitation of imputation. A big percentage of your data is missing. So for NCA software options, here I laid out the various stages of the workflow. So data preparation, analysis, statistical analysis, and reporting, and like Microsoft Word or open alternative open source tools. So many times we use like Excel to build a database, maybe R for the coders or Stata, and for the analysis, the industry standard is Winolin, but it's not open source or free. And then we have the open source tools like R, PKNCA that doesn't have an interface, so you need to be able to write scripts. And we have the PK Analytics, which has an interface and which is made available to PMX Africa. So I will show it. And some companies have their own custom code in SAS or Stata or any other tool. So that's what we'll focus on. And of course, once you did the analysis, you will have to do maybe statistical analysis, your preferred software, Stata, SAS, Phoenix, R, etc. Okay. And here's just a quick example of what this table or reporting. It can be like simple, but you need to show the assumption. So that's a table that I took from Phoenix in Norman. So you can have footnote and say this guy didn't meet the square adjusted, and this guy was excluded from summary. So you need enough documentation about what happened in your data and how you did the computation. And now we arrived to the exciting part, which is like the demo, which is live. So here you have your, I have two files I will show, the NCA2 profile, which is a toy 2 profile example. So that's like really two profiles. So what I did is I copy pasted, or I saved so yeah, basically I saved as Excel. It came as CSV, but most probably your data will be built in Excel first. So here, instead of this format that's like common in POP-PK, if you want, I copy pasted and showed, okay, I have ID, time, and here we have two periods in same ID. So I had this concentration here, and I did a plot. So this is just to show you that, yeah, Excel can be used to, say, do some quick EDA, you do some plots. You see that this point is weird, so you might want to delete it and see, okay, or undo, and question this data point when you go back to the clinic and see if it's really correct, for example. So when, and in the materials, I have also an Excel sheet called NCA Excel, just to introduce it to the computation. The same data as before, the time point, the data, and like control and test. So here you see this weird point, I didn't exclude. And it's a fictitious drug interaction study where we have given fluconazole, a huge inhibition to like a huge increase in AUC. So how do we compute NCA? So as I mentioned in the slides, you compute the average of consecutive concentration, and you compute delta time, and you multiply, and then you have the sum of each section. So AUC 0 last is really the sum of these slices, consecutive slices. So it's relatively simple computation that you can do, and you will have access to Excel. And for the slope here, I'm using an Excel function called slope. And then you tell it what times and what concentration. So here it's a log linear regression. So the Y will be log of concentration. And here I excluded this point by just having a blank. So that's my way of excluding Excel. So if you don't want to exclude, so that's like, you see the slopes changed a little bit, not too much, but I'll keep it empty here. And same computation in this part, and you can compute clearance, dose over AUC, and so on, the half-life. And at the end, you want like to interpret, that's really what's important. Once you've done NCA, which is usually the straightforward part, the easy part, you want to think in a clinical pharmacology way and say, okay, what happened to keep half-life the same, almost not change, while Cmax is increased threefold and clearance was reduced by 60%. So, so that's what's really important to think about when we do after we do NCA. So, and to show you the equivalent, so here it's I open PK Analytics, and I will go to just upload same data, NCA to profile, open. Because I'm not using standard names, I need to tell it, oh, this is an ID, that's an occasion, time, observation, all good. So you click on plot and you see, okay, yeah, that's a two profile, and then you can tell it, okay, these are the various AUC methods, and you can run a quick NCA. So to run, and let us see if we get the same or similar results. So AUC all. So, okay. So we have 57605, exactly same. And we have here 127051, up to the second digit. It's very simple computation. So we get exactly the same result. And if we use the same rules for lambda z, of course, we'll get the same result. We'll show you that, yeah, you will get. So here in task, if you go to lambda z, by default, it uses all this point. You can change the time range here, apply, and you can say, I will include this point and unselect this point. So now it becomes gray, not blue. Apply. Now it only did the regression here. So it's very simple and quick and straightforward to change the rules if you want. And once you are happy with the rule, you rerun your NCA, and you will get your summary. Here you only have to profile and individual. So that's to illustrate with simple true data. And I'll keep this for the questions, but I wanted to cover the rifampicin, at least give you a flavor on it, and hopefully we'll cover it in much more detail with the on-site courses, various on-site courses. So here, that's a study, as I mentioned, that Dr. Colin Pillai forwarded about the quality assurance of several fixed drug combination in South Africa, comparing their availability. So you will have a copy of the PDF. It's we have a reference formulation and two other. So you can read it and understand more about the design. But if we close this, I will open again PK Analytics just to show you that. So I'm opening a new project, completely new one. So new project, browse, show you how quick it can be. So I'm loading the refund data. You need minimally to tell it, okay, what is what for non-standard names. So ref is a concentration for it. So observation, that's categorical, and so on. That's AMT not detected, BLQ, accept. Now you can see that's one of the snapshots I showed. And like, for example, if you want to stratify, you can just split by form. So yeah. So once you do some EDA, you can run the analysis. So here I will show you, okay, maybe I want extrapolated, extrapolated AUC not to exceed 20%. That's one of the rules. And then so I run the analysis. I got the individual parameter, the summary table, and let's see. Yeah, this guy, we couldn't compute NCA parameter 9.1. We'll see in a minute why. So let us go to task and Analyses. So these are the results of the profile. And so you can see that this guy here, the concentration were going up. So we couldn't fit a terminal phase. That's why we couldn't compute like lambda z or half-life and so on. So you see here. And maybe one of the rules you want is not to include Cmax because we know that absorption won't be finished. So you might want, okay, for this guy, I'm using only the last 3 points. Apply. You might want to check. Oh, here we also included Cmax. Stuff like that. You run, rerun very quickly, and you get your estimates. So yeah, I don't want to remove any possibility of question. So hopefully with the on-site course will cover like this also open source tools like the GG Quick EDA. And here just as a preview, I included a slide on some other African data on living climate, very interesting one showing that and that snapshot from GG Quick EDA showing that increasing libin dose beyond like 5 milligram is not really improving or reducing glucose. So very interesting data that we'll cover hopefully in the on-site course. Adini, maybe we can now allow some questions.
Oh, thank you, Samuel. This is quite instructive. We appreciate this, lots of information. So in case you have questions, please put it in the chat box and we can use a couple of minutes to address those. Maybe I should call attention to 1 or 2 questions that we've received. Even if we've made comments, maybe you may have some additional comments. One question is, what are the advantages of NCA over compartmental analysis? Do you have comments on that, Samuel?
So yeah, the NCA involves like assumptions and it's can be automated and basically you can run your NCA say in a few hours. While for modeling, there's a lot of assumptions involved. It requires much more effort and time. The advantages of NCA, you can get very quickly your valuable PK parameters, say your AUCs, your half-life, your clearance, and then generate insight. Of course, if NCA assumption hold, like you have like rich PK, like compartmental modeling or pop PK, you can have very sparse data. With adequate prior models and knowledge, you can still get valuable information from it. But for NCA, you need full PK profile. You can't like have few troughs and then run an NCA.
Yeah, thank you for that. Another question on how to get PK Analytics or license has been nicely addressed by Haida. So Haida, thanks for that. A second question, a third one, how to deal with missing data in NCA and how could it affect the EDA interpretation. I think you partially addressed that, but do you have any additional comments? How to deal with missing data and how it affects the interpretation of the EDA?
Yeah, so basically, like missing data, why it's missing in a sense. One common, say, source of missing data is when it's BQL. So it's reported depending on like your database. It might be reported as just below BQL, or sometimes it's really a missing sample. It never happened. Like the nurse didn't, or the sample was destroyed somehow. So that all can happen. So how to deal with it? As we do in other statistical analysis, you can just ignore it, pretend it doesn't exist. Or you can impute, say, replace the missing data by a value that you think is most probable, like BQL over 2 or a 0, if it's early in the profile. And as I mentioned, if you have a lot of missing data, you might resort to modeling this missingness, like we do in PopPK. We have the M3 method or M4 and so on. And one more comment about missing data. For example, maybe you have a missing covariate. So if you want a summary by, say, women and men, maybe you will have another category missing. It will be n equal 1, but it will be excluded from the summaries. But that's similar to all kind of analysis when we face missing data.
Yeah, thank you. And then lastly, there is a question. Sorry for the interference from one of the attendees. Now, the last question here is, would you suggest that NCA is an obligatory first step before you do compartmental analysis? And when can we say or argue that NCA is sufficient without the need for compartmental analysis?
So, okay, there was two parts. When NCA is sufficient, but this first part, what was the question?
Yeah, that is NCA always necessary before you proceed for compartmental analysis?
Well, let us see it this way, like NCA can give you a lot of information very quickly and provide you some hypotheses and some good initial estimates. Say, you know, your range of clearance, you know, volume, you know whether you have some dose dependency, for example. So I would say it is an additional it's helpful for you before modeling, whether you did the NCA yourself or whether you read an NCA report that your ClinPharm colleague has run. It's always very informative and very valuable info before modeling to have a look at, to do NCA or have a look at prior NCA. So, and as I mentioned, many analyses rely only on NCA, like the food effect, for example. You might have a dedicated food effect study, you run NCA and ratio assessment, and it will be sufficient for your label claim to be based on this dedicated study. Now, of course, having dedicated study can be time consuming, very expensive. So you thought, okay, why not I plug a food effect component in my MTD protocol? That happens. I've seen it many times in oncology. But depending on study design, you might not be able to do NCA. You want to model data and have like a model-based food effect, for example. So I would say it's very straightforward to convince the authorities and everyone when you have like a dedicated NCA type of results. But sometimes you can rely on modeling when you don't have the data for NCA. I can think of a submission where, say, we only did modeling with zero NCA. And in our days as well, very, very rarely did I see a submission with only NCA. There's always some modeling component which enable you, for example, to simulate, to extrapolate what happens when we change the dose, what happens when we change the dose interval, what happens if clearance was varying over time. So you can explore many, many scenarios that with NCA you can't explore. That's the value of modeling.
Yeah, thank you for that. Not sure if we have any additional comments from other faculty of the Pharmacometrics Africa attending. Colin, either?
Colin, no, nothing from me. You go ahead.
So Nii, no further comments from me. Thanks very much, Nii, for excellent facilitation, and Samir from your side for taking the time to do this.
It's a pleasure. Thanks, Colin.
Thank you. Thanks a lot, Samir. And we truly appreciate all the participants who joined today's webinar. And like we mentioned at the beginning, the recorded webinar will be posted on Pharmacometrics Africa website in a couple of days from now, and you'll receive emails to that effect. So we'd encourage you to look out for further information on the series of activities hosted by Pharmacometrics Africa and sponsored. In addition to that, we encourage you to share the webinar once you receive the information. So thank you once again. I'm looking forward to welcoming you to the next one.